which is supposed to be on week 11, but we have done up to the rigorous method last week. So today I'm going to continue to the batch reactor. Okay, so batch reactor means that nothing goes in and nothing goes out. You only put in the input once. Okay, you only feed the input once, you process it. Once it's done, you take it out and then you put back another one, meaning that the feed in and the feed out is equal to 0 and the volume is constant. That's what it means, batch reactor. So now usually the batch reactor is used for small volume production, for example, and small volume production and expensive production. Okay, for example, specialty chemicals such as drugs, it is expensive, and pharmaceutical products, so it is expensive and they have to carefully process it. So we use the batch reactors instead of batch reactors instead of a continuous reactor. Okay, and also if you were to process the polymerization process, for polymerization process you cannot it will take some time for the polymer to grow. Okay, so you cannot actually use the continuous reactor because it will go in and it will go out, then you don't have time for the polymerization to take place. So what happened is that usually they put it in a batch reactor or a semi-continuous reactor, so that it will give time for the residence time is going to be long, and it will take time for the polymerization process to occur until they reach the certain mass weight they want. It starts from monomer going to dimer, duplicate, triplicate, until it becomes a polymer with a certain mass weight. For example, you want the mass weight of 2000, 20,000 mass weight, then after that you stop. So but how do you decide when to stop? Okay, so you can actually look into the modeling part to decide when to stop. Usually the prescribed formula, kalau you kerja dekat industri, what happens is that you are following the formula passed down through generations. Sometimes when you are working, you don't even know why it's like that. You know why at time after 1 hour you have to stop the operation and take out the product. You don't even know. But how do they decide to do that? So this is how they decide. Okay, it's a very suitable for slow reaction. For example, yang macam I sebut tadi, for batch processing. Okay, very for slow reaction, and then you can actually optimize the operation once you know what is the yield and that you want from the process. Okay, so this is what it looks like. First, the reactants are charged into the reactor. So this is the reactor, this is the process fluid. So these are the jackets. Okay, the jacket. Now they charge the reactant into the system, and then they close this valve until it is full to the volume that you want. So after that they start to, okay, this is actually this is the wall. So this is your reactor wall, this is actually the jacket. Okay, so now they need to actually increase the temperature of the reactant, so they feed in the steam. This is initially cold, so when the steam in touch with coal means that your Q is going inside. Okay, then you will expect some of the steam will condense to become water. So this is actually where your condensate is collected. Okay, now once your Q it has reached to a certain temperature, okay, once it has reached a certain temperature, this has to be stopped because the reaction start to go to to continue in here. When the reaction starts to continue, means that you have to control the temperature. Say for example, this is exo process. So if this is exo process, then you have to bring down the temperature. So the only way to bring down the temperature is when we have to start to pump the water. Okay, they start to pump in the water just to actually control the temperature, and this is the cooling water out. So we keep the process until that we know the time when we have to collect the output from here. So once the temperature has reached, what we do is that we stop the operation and we take this one out. So these are all actually the explanation of what's going to do. But the thing is that now the reaction in here that takes place is going from A to B and going to C. This is our desired product. This is our undesired product. So if we let this temperature, if we let the reaction going on, okay, just on and on, you will have a lot of C. You don't have much of B, because B is the reactant to produce C. So what happens is that you must know the exact time to stop the reaction. And A going to B is following the K1 specific reaction rate, and from B to C following K2 specific reaction rate. Okay, next. C is the undesired byproduct. Okay, and these are all the explanation I have actually explained to you just now. Okay, we have to determine when is the optimum batch time required to obtain the highest yield of the B possible, because B is your product. So you want to know when is to stop. You have the highest of B, you don't have much of C. Okay, you can what can be done is you can actually quench, sudden cool of this process. Why we sudden cool? Because when we actually quench it, then it will start to, the temperature start to go down. Just now I cakap tadi, the temperature start to go down, and then after that your K is depending on the temperature. Okay, it's K is actually alpha exponential minus EA over RT. Your K, this one, is depending on this. So when we this one has some range of value, say for example between X and Y. So if you reduce the temperature to a low temperature, quench mean that it's a sudden cool. So when you actually reduce the temperature to the sudden temperature, then your K will be slowed down. Then you can stop the reaction. Okay, so the question is that when to quench the process fluid. So that's the thing that you have to figure out. So in order for you to do that, what you can do is that you can actually model the equation. Okay, model the process there. So that is the conditions that we have to consider. This is only a general guideline. So if dependency on of T on both K1 and K2 is the same, means that the both Ks have the same activation energy, the reaction should be run at the highest T to minimize the batch time. Okay, because now remember what you want to do is you want to have your B. You don't want your C. You don't want the C. Okay, so this is what you want. So if your K1 and K2 is the same, then the reaction should be run at the highest T to minimize the batch time. Then but however, your highest temperature is depending on certain conditions. You cannot run it too high, because when you run it at too high, then you can actually destroy your product, because your product has a temperature it can stand, where after that they degrade or sublime, everything evaporated, you cannot actually get the product. The molecules breaks out. Okay, the molecules breaks up, then what happens is that you don't get the product because the temperature is too high. Or you have to remember the maximum working This is not pressure, but the maximum working temperature of your metal, of the metal wall. You have to remember that. So the same goes if you, when you are doing simulation for your in distillation column. Remember, you have a reboiler at DC. So make sure when you operate that the temperature of the reboiler, when you simulate it, make sure it is actually below the degradation temperature. So you have to actually determine the compound's degradation temperature or decomposed temperature, degradation or decomposition. That's the term we use. Okay, so if the temperature is higher than the decomposition temperature of the compound, then your compound will actually destroyed. Okay, so how to bring the temperature down? What is other parameter that you can actually set dekat you punya distillation column so that you can bring the temperature of your reboiler down? How to do that? Huh? Say it again.
Number of stage.
No. Number of stage will determine the efficiency. We are talking about the reboiler in the distillation column. Sama lah macam case ni. Because you have to run the temperature kan, the high temperature in order for the separation to occur. Okay, to have a better separation, but you cannot exceed the degradation temperature. So how are you going to bring down the temperature, but the separation still can occur? The parameter that you can change, anyone? Pressure. Because when you actually decrease the pressure, the temperature will decrease. So you can actually always work with vacuum condition. Okay, when you work in vacuum condition, then the temperature of the boiler will decrease. Then it won't affect you punya component, because the degradation temperature is lower than the component's temperature. Okay. Okay, that's one of the hint how to do your DC. So if your K is more temperature dependent than your K2, what do? You also will run the process at the highest possible temperature to favor reaction to be. So tadi if your K1 and K2 is almost the same, the dependency on temperature almost the same, maknanya when temperature tu berubah, the rate of the K berubah pun is the same. Okay, of both K1 and K2, then you run it at highest possible temperature and you bring it down. So the same goes in here. If your K1 is lower than the dependency of K1 is more, if the K1 is more temperature dependent than the K2, you run it at highest possible temperature first. Then but you have to determine when to stop the reaction through the CCE and energy balance. And since the volume is constant, you don't have to use a product rule, right? Okay. If your K2 is more temperature dependent compared to your K1, means that you will have to start off at the highest temperature to get the first reaction going. So remember, A going to B, going to C, you have K1, you have K2. So if your K2 ni is more dependent than K1 on temperature, kita ubah sikit temperature, K2 naik. Bila K2 naik, means that more C will be produced. That's what it means. Okay, so when this happen, you run it at a start off at high temperature to get this one going, because this one has to proceed first, then drop it to prevent the loss of too much of B. But it does not really matter. You don't have to remember this, because when you're working later, you don't have to remember this, because this is only a general guideline. So what you need to do is that you have to know what is your K1 and your K2. After that, do your balance. After that, solve it. Then you know. Okay, you can actually simulate. You put in what is the temperature in first, and then blah blah blah, then you see what is the best possible time for you to take out the product. Okay, I'll see. Okay, now say for example, we have done our CCE. Okay, you have done your TCE, your CCE, and your energy balance. Now in this case, your volume constant, you don't have to worry about this. Everything is from your TCE, dV on dt is equals to 0. Okay, now you have to worry about your CCE and energy balance, because your temperature will actually affect the yield. So what we do is that from your CCE, okay, you have to do the balance for all the three. Say for example A, because A going to B going to C, so you want to know how does your A, B and C change with time. So from here, if you run the CCE, you will have dCA on dt, dCB on dt and dCC on dt. So from here you can actually use, say for example, Euler method, right, to find the profile of if temperature is equal to 0, what is your CA, CB, CC. That's the start of the operation. So when T is equals to 1 hour, T is equals to 20 minutes, because this is liquid, it takes us longer time to proceed. So T is equals to 20 minutes, what happened to your CA, CB and CC? Okay, so you can use Euler method or Runge-Kutta method. Then after that, at the same time, you have to solve your energy balance. You have to solve your energy balance, so that, and then you plot it on the same graph. So because remember, this one is your T, this is your T. So you plot it on the same graph, then you should be able to get this. Okay, you can actually guess what is your T. Your first T would be your T initial when you feed in the your feed you punya reactants. Say for example, this is at 30 degrees Celsius, and then you bring up the temperature, and then what happened when the temperatures goes down? This one will go on with this is when you pump in the coolant, the cooling water. Okay, so these are the region when you have steam coming in, the steam plus the exothermic reaction. You cannot let the temperature to be too high, or else you will degrade the product. So that's why at this point you must know what is the degradation of your product, the temperature. So at this point you start to cool it off. Okay, so when that happen, then when you plot this one out, you will know your the CA and the profile of CA, CB and CC. You can imagine this, right? Because remember, in your energy balance, okay, in your EB, there's an expression for K there. Remember? It's minus lambda V K C A, and then especially when you have this, then you have to take care of A, your B and C, K1 and K2 and so on. You remember that, right? You can imagine that. So once your K is there, means that the energy balance is tied to your CCE. How does the CCE change will actually impact your temperature, and that will actually affect what is the rate of the cooling water that you pump into the system to cool it down. So this is an example of the relationship. Okay, now say for example you have done the CCE, the energy balance, okay, for the system. You have drawn this graph, you got this. Then how do you decide when to stop? How do you decide when to stop? Okay, this graph suggests this is the point, the T optimum. Why? Because at this point you have the least of your CA, the CC is about to pick up, but your CB level off here and about to go down. Remember, you want your CB, you don't want too much of CC, because this is your CC is your undesired product. So what happens that, okay, this is when you have to stop. You know, this is the temperature, the final temperature of the water. And when you have actually determined your T, and this is actually your tau, yeah, the residence time, this is the same thing. Okay, this is your T and the tau is the same thing. So then you stop the operation, you quench it secepat mungkin. This one is quench the temperature. After this, it has to go down like that. So once it is quenched, we know we stop the reaction there. Okay, and that's it. Then you can take it out. This is how they decide. Dia bagi the prescribed formula tu dekat the industry. The consultant are the one who do this, and then they build the plan for the stakeholder, and the people start coming and working. Dia bagi, nah ini dia, this is the prescription, you ikut aja. So there are so many engineers, when you go back to your when you go and work, you always want to go back to university, in touch with your alma mater, because you have forgotten what you have learned. That's what I learned from the alumni lah, your alumni. They have forgotten what they have learned. They just go to the industry. They gain more experience on how to control things, blah 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 blah. But that through prescription. Just if the temperature this one goes up, okay, you reduce this. If this pressure goes up, you reduce this. If the yield is going out like that, you reduce the temperature. But they do not know how you got that. Okay, so this is how you go back. Jangan buang, jangan. I tahu you tak ada buku ni, but jangan delete you punya soft copy buku ni pun you nak delete, nyampah dah, tak larat dah. Don't do that. Okay, you might want to flip through and read here and there, so that you still can remember how you got that prescription. Okay? Alright, good. What you are going to learn, what you are going to face in your design project is a very valuable lesson for you. You can see the overall picture. It can be just an appreciation of the process. Definitely when you're working with industry later on, when you're working with a consultation firm later on, it's not going to be that simple. Petronas, they kan ada PRSS, I don't know, Petronas Research Center. They do energy balance, they do the simulation, but when they do the manual calculation to prove the simulation, it took them 2 years to do that, because they go every detail. They take care of the activity coefficient model they use. They take care of the fugacity, the equation of state they use, and calculate through that using Excel to prove the simulation values. Took them 2 years. We cannot ask you to do design project 2 years. You are going to graduate in 10 years from now, so that's too long. So it's only an appreciation of the process. So cherish the moment. Jangan rasa you didera. You will remember that. I still remember the process of the design project process for my group. It was like 20 odd years ago. Okay, I remember the part when the Mak Saleh tumbuk another Mak Saleh lah, of course. Because they cannot stand working together. So because what happens that they combine the whole group ni, ada yang okay, ada yang tak okay kan. Not really. It's like they don't do that. What they do no, it's like from those yang first class sampai third class. So from that they ambil chunk the region of the first class, second class upper, second class lower, and then dia combine. So those yang the higher marks, so they couldn't stand orang yang bawah sikit je daripada dia. So what really happened is that guy likes to party and so on, does not do his work. So I'm macam, okay, goodbye, I'm not going to go into that. Your fight of yours. Okay, so I believe you can do this. Yes, this is easy, not difficult. Let's do one for B. Why not we do one for B? This is an example of consecutive reaction. So we have dCB on dt is equals to what? F. We want B, okay, now it's like that. No, there's no in, there's no out. So there's no F coming in, and CB naught minus F CB. This one tak ada, this one is 0. No in, no out. But this one is very much depending on your rate of consumption, okay, and rate of production. So that is minus VK1 CA, right, and plus VK2 CB. Yeah, this is very simple. So for batch reaction, oh hang on, this is you have your V there. Okay, I forgot that. So when you have this, means that you can actually cross out your V, and you have your dCB on dt equals to minus K1 CA plus K2 CB. Okay. Very good. Okay. Now the same goes to C. So when we want to do the balance for dCC on dt is equals to F naught CC naught minus F CC minus V K2 CB. So we cross this one out because this is a batch reactor. Then we cross your volume because it's a constant volume. So we'll have dCC on dt equals to minus K2 CB. And remember, you have the kinetic equations. Your K1 is actually alpha exponential minus EA over RT, and the next one you have your K2 is equals to alpha exponential minus EA over RT. Okay, so you plug in these values inside this, and you plug in these values inside here. This one is in here, and after that, this is how it is tied to your energy balance from the temperature. After this, you have to do your dt on dt, right, from your energy balance. So you solve for T first. So once you have this, then you can actually solve for your CC and CB. Okay? Yes?
Temperature tu dia depend on K1 jadi T1 ke constant?
The temperature is constant because everything happen at the same time in the reactor. It depends on the temperature of the reactor lah during that time. You remember, you have to quench it, right? You have to have the formula, the right formulation, when to quench it, when to actually starts to slow down. Because when the reaction starts to occur, when it starts to for example, polymerization process, it is an exothermic process, so the temperature keep being released out. So when the temperature is released out, what you have to do is that you have to bring it down to a constant point, but it has to gradually decrease to finally stop the reaction. You cannot even though you quench it, you memula dia ada a certain temperature, and then you quench, you put in like minus 20 punya temperature, still it will have to take down. Okay, it will take time for the temperature to bring down. You imagine, because it's not a small glass we're talking about in the house. We are talking probably about 60 ton volume of the reactor, or 20 ton volume of reactor if it's a small reactor. So when we talk about that, means that it will still take time for the temperature to go down. Remember, you have a stirrer. Stirrer will make sure that the temperature is evenly distributed throughout the whole system. But however you cool it off pun, because the cooling off tu is like at the circulating the vessel, you cannot put just like ice inside, you see. So still it will take time, and it will, once the temperature goes down, then it will still affect your CA, CB and CC, the profile of your graph too. That's why you must have a correct timing, what to do, what is the temperature, the energy balance of the jacket, and energy balance of your of the process fluid. So the one that is shown here, this is actually the temperature of the process fluid. Imagine you have to do the balance for the energy, you have to do the energy balance for the process fluid and for the jacket to understand the profile, how fast it can actually reduce the temperature. You understand what I'm trying to say? Yes? Yes, you understand what I'm trying to say? Orang-orang kayangan, dewa-dewa. You understand, eh? You Faham Okay. Okay. I penat cakap ni. Nanti ke. Okay, now. To be detailed. Okay, I told you just now you need the equation dt on dt for process fluid. Okay, for the process fluid. Then you have to have the and if you want to be detailed, then you can assume you can actually do energy balance for metal wall. dt m on dt. Okay, now you need to have two equations. Remember, you have heating system and the cooling system. Now you have to do the dt steam over dt and dt water over dt. Now you join these two. Okay, when you have the graph like that, this is your process fluid. This is the profile of your process fluid. So on top of this, what you have to do is you take the profile of your steam. I'm sure it's like that. Okay, and the cooling water starts probably from here, going like that. Probably. I've never tried to solve this, but we can actually always imagine that. Yeah, because we want to bring down the temperature of your process fluid. This is the temperature, yeah. Okay, this is water, the cooling water, and that is the steam. The steam will be cool off a little bit until it becomes condensed, because it is in touch with something cold at the beginning. When you want to start off the reaction, mula masuk at 25 degrees Celsius, and after that you increase the temperature so that the reaction can proceed. The reaction has to proceed at the certain temperature range. After that, when its exothermic process is going like crazy, you have to maintain that temperature. After that, when you think that it's about time to actually collect your product, you have to pump in the cooling water more, quench the process so that it will gradually decrease. So you have to tally all this profile with your the component continuity equation, the profile, the off change of A, B and C, so that you will get the optimum process condition for you to take up the process. You understand what I'm trying to say? Yes. So all these equations need to be solved at the same time. Don't worry, you have Excel to do that. So please make sure you tak buta Excel when you go out from university. Make sure you know how to use Excel, or else you'll be a laughing stock. Trust me. Excel is a kind of oxygen, semi-oxygen for chemical engineers, for engineers actually. There's no way for you to solve everything using manual calculator ke program calculator. No way. That is the simplest software. Please make sure you know how to use them. End of lecture, but not today. I'm going to continue another 1 hour. So you please take like 5 minutes break, then you can come back. Lepas ni tak ada kelas kan? Lepas pukul 10 tak ada. Jangan tegar buat kelas I cannot afford to miss it because I'm busy. I tak ada masa nak ganti. Faham